Okay, it looks to be recording again. So imagine you had like a L-shaped bathtub like this, and then you put 2 feet of water up here and 1 foot of water down here. So you have twice as much water up here than you have down here. This is okay if there's a barrier, if there's a wall holding this water in. So we could put 2 feet down here and then 1 foot of water up here. So we'll have twice as much water here. So some people think of resonance as like this. It's resonating 2 feet, 1 foot, 2 feet, 1 foot. And the same thing here, 1 foot, 2 feet, 1 foot, 2 feet. So this would be resonating up and down like that. Is that what we see? No, that's not what we see, because what happens is there's no wall separating the water. In fact, the water can flow in either direction. If there's no wall separating the water, is this sustainable? No, well, what's going to happen is we're going to have a 50-50 mix of these two. And the reason is there's no wall. If there's a wall here, then we can isolate the two sides of the tub. But there's no wall there. And so, in this case, this is localization versus delocalization. We could localize 2 feet here, but we got to make sure it's localized. That is, there's no way for it to go. We could localize 2 feet here, but what happens is it's going to be delocalized. That is, the whole electron cloud is going to spread out. And it's going to spread out because there's no wall holding the water. There's no wall holding the water. What can happen here is that the electron density can move. So if we start off with this structure, we take this lone pair, make a double bond here, and then kick out this double bonding pair and make that lone pair here. We end up with this structure. And then we can go backwards here. That is, we can just take this lone pair, drop it into the bond here, and then kick out this lone pair here. And so we could go either way. In other words, the electrons are not localized, they're delocalized. That is, they can move. And so the electron cloud is like water. It's going to spread out in the structure. And so electron clouds are like water. It's going to spread out in the structure. And so the way we're going to draw that is like this. We're going to draw the double bonding electrons as being spread out in the structure. And so each of the oxygens will be singly bonded to the carbon. And then the double bonding electrons will be spread out like this. So what results is not a double and then a single, but what results is what we call a 1.5 bond. So this is a 1.5 bond. A double would be 2, a single would be 1. This is a 1.5, this is going to be a 1.5 bond here. Then there are 2 lone pairs that are localized on each oxygen. Those aren't spread out or shared, but there's 1 lone pair that's distributed over both oxygens here. So I'll draw as dotted. And so the charge that results is not 0 and negative, and it doesn't fluctuate 0, negative, 0, negative. The charge that results here is a -1 charge distributed over 2 oxygens. So we get -1 over 2 oxygens, which gives us a -1/2. And a -1/2. And so this is what's observed experimentally. You know, experimentally, what's observed are the 2 bonds are identical. You can't tell the difference. And so it's not a double, it's not a single, it's a 1.5. And then the charge, the formal charge on the terminal oxygens here is the same. -1/2. This was kind of done after the fact. You know, when you draw these resonance forms, it doesn't quite match what's observed experimentally, so they came up with this idea called the resonance hybrid, and that's what we show here, the resonance hybrid being the most accurate depiction of the structure. So this is the resonance hybrid. We can do the same thing here. We add up the sum of the formal charges to get the net charge. Net charge is -1. So I forgot to write it down, but note resonance forms, atoms stay stationary. Atoms do not move. So one of the most common mistakes in drawing resonance forms is people will tend to move the hydrogen. So they'll put the hydrogen here, and then they'll put the hydrogen here, and then they'll put the hydrogen here. We never want to move the hydrogen. In fact, we don't want to move any of the atoms. The only thing we do is redistribute the electrons. Have you heard of ad hoc? ADHOC, ad hoc? Ad hoc is something you tack on at the end. So we come up, we draw these resonance forms, and then it doesn't quite match the experiment. And so you come up with a new idea. The new idea is the resonance hybrid. And so that's an ad hoc attachment after the fact. Ad hoc analysis. All right, let's go on to another example, H2S. What we're going to do with H2S is we're going to do a more thorough valence bond analysis of this. So hydrogen, we have 2 of those, that's 2 electrons. 1 sulfur, that's 6 electrons. So altogether we have 8 electrons. In this one, the skeleton we're going to draw is an HSH. Hydrogen can never form a bridging scenario. It's never a central atom. Sulfur can. And then we've used 4, and we'll just complete the octet to the sulfur. That's 8. We have H2S here. So in valence bond theory, a bond is the overlap of atomic orbitals. And so let's take a look at the atomic orbitals here for sulfur. Sulfur is the 3rd shell or 3rd period. And so we're going to start off with the neon core and then just look at the valence electrons. Looking at the valence, we got the 3s and the 3p here. Altogether, sulfur has 6 valence electrons. 1. Now, Aufbau says, what do we do with that S? We fill it first. Aufbau principle says fill the lowest energy orbitals first, and then 1, 2, 3, 4, 5, 6. That's it. So right off we see that sulfur should only form how many bonds? It should only form 2 bonds. Here, let's say I tried to bond to this s orbital. So hydrogen comes along and tries to bond here. What's the problem with hydrogen coming to bond there and sharing electrons? This orbital has 2 electrons it could share. Well, hydrogen only needs 1 electron to share. Is there a problem with that, putting 3 electrons in an orbital? Yes, that's a violation of what? Pauli exclusion principle. It can't happen. We can't put 3 electrons into 1 bond. And so when I look at this, we can form a bond here, and we can form a bond here. So sulfur would like to form 2 bonds here to the hydrogen. And so hydrogen's going to donate 1 electron to the bond, and the sulfur is going to donate the other electron to the bond. So I'm not going to draw the core orbitals. We're just going to look at the valence orbitals here. And so, I'm going to draw one of these. I'm going to call this orbital this. So the 3p orbital here.
These people look confused.
That'll be this one here. This 3p orbital has 1 electron in it. It doesn't matter which lobe. It could be in the upper lobe or the lower lobe here. It doesn't matter which lobe. But it has 1 electron in the orbital. The orbital consists of 2 lobes. And then hydrogen has a 1s orbital, which is going to come in here. 1s orbitals are quite small, and that has 1 electron in it. And so this is for hydrogen. I'm not going to write an H in the center there. And so we created a valence bond. A valence bond is the overlap of atomic orbitals. When we're overlapping the atomic orbitals, we get increased electron cloud density here in the overlap region. So there's increased electron cloud density here compared to out here and here. And so what holds the bond together are the positive nuclei being attracted to this electron cloud that sits between the 2 nuclei. Those positive negative attraction. Then we have another bond here. And that's going to take another p orbital. The p orbitals are orthogonal to one another, so they're at 90-degree angles. So this p orbital here, I'll draw like this. I'll throw 1 electron spin up in this 3p orbital here. Okay, and then a hydrogen can come along, a hydrogen with this 1s orbital in overlap here. So this is the other bond here. Again, the bond is going to be an electrical attraction. Oh, shoot. When somebody comes in, it loses track and tries to track other people. You'll be on the video.
Maybe you should just want that more heavy.
In the back, yeah. If you don't mind. I'd rather not have to edit it. Is it all right? Yeah, okay. Okay, again, in the overlap region, here we have a higher electron cloud density than over here in the non-overlap regions. So this is going to concentrate negative charge here, which is going to hold the atoms together. And then we labeled the bonds. Let me just tell you what the labels are on the bond. So this is called an sp sigma bond. Or we could call it a 1s 3p sigma bond. Either way. And this is another 1s 3p sigma bond. Or just an sp sigma. Depends on how descriptive you want to get. All right, there is another p orbital. That p orbital is going to sit perpendicular to the plane. Here, I'll draw it a different color. Sort of green. I have a lot of colors today. So we have another p orbital which is perpendicular. So one lobe comes out of the plane of the page and the other lobe goes in. This is going to have a lone pair here. And then we have the S with a lone pair here. So let's draw the S. This is the 3s orbital. And that's going to have a lone pair like this. So the shape of this depends on how the atoms are arranged in three-dimensional space. So I'm going to try to draw this out. I'm going to have one hydrogen bonded straight up like this, and one hydrogen bonded out like this. And then I'm going to have a lone pair in the p orbitals, which kind of project out and in. And then I'll have another lone pair in the s orbitals like this. And what I expect here is I expect the H-S-H bond angle. So the H-S-H bond angle, what do you expect that angle to be? I expect it to be 90 degrees. And that makes sense because the p orbitals are oriented 90 degrees relative to one another. And so the bond angle should be 90 degrees. But whatever theory says has to be confirmed by experiment. And the observed angle is about 90 degrees. It's like 92 degrees. It's pretty close. And so that's consistent with our theoretical analysis of this. So that's H2S, hydrogen sulfide. Let's do H2O, water. Essentially the same thing, except it's second shell or second period. It's the same thing. So we expect a 90-degree HOH angle. Is that what's observed? No, not even close. What's observed is closer to 109.5 degrees. Actually, it's 104.5 degrees, roughly. But we'll just say it's close to 109.5. It's hugely off. So what needs to change? The bond angle or the theory? What needs to change is the theory. Should we just throw away all this quantum mechanics? No. So what we're going to do is we're going to add something to it. You know what we're going to add? This is after the fact. After the fact, you realize, hey, it's not working.
Is that good science?
Yeah. If it's not working, then you change something in the theory
I get that.
to make it work. But in a way, no, because they should have derived it initially. So, and after the fact is not the best way of doing it. So this is ad hoc addition to quantum mechanics. Well, we're going to say that we can't make H2O using the same orbitals that we did for H2S. And so what we have to do is we have to introduce some new orbitals that we're going to use. And these new orbitals are going to be called hybrid orbitals. And so first let me tell you the hybrid orbitals that we're going to be dealing with. We have the sp hybrid orbitals, which there are two of them. And so this would be the valence orbitals here. We have the sp2, which there are three of them. And that leaves one p orbital left over. We have the sp3, which there are four of them. They're all equal in energy. There are no p orbitals left over. Then we have something called the sp3d orbitals. There are five of them. Each of these are an sp3d, 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 sp3d. And then there are 1, 2, 3, 4 unhybridized d orbitals here. And then we have sp3d2 hybrid orbitals. 1, 2, 3, 4, 5, 6. There's 6 of them. Each of these will be an sp3d2. And they're going to be 3 unhybridized d orbitals left over here. So this is a modification to our normal unhybridized atomic orbitals. These are hybrid atomic orbitals. And so these hybrid orbitals are brought up to explain things like water. So a couple of questions come up. Why hybridize? There are two reasons we do this. One is to maximize bonding. Maximize bonding, we may or may not have to hybridize to maximize bonding. Two is to minimize repulsions. So here we have to do it. In sulfur, the p orbitals are huge. These are 3p. They're big. In oxygen, the p orbitals are quite a bit smaller because these are 2p orbitals. When we have the smaller orbitals, there are going to be greater repulsions than these bigger orbitals. Because if I throw an electron here in this p orbital and an electron here in this p orbital, they can spread apart from each other. But when you compress them into small orbitals, then the repulsions are greater in smaller atoms. So, this is what we're going to do. We're not going to worry about is it hybridized or unhybridized. Like, for example, H2S is unhybridized, H2O is hybridized. We're not going to worry about that because you don't exactly know at which point, does it get too small. And so we're just going to hybridize everything. And the hybridization is going to depend on how many groups of electrons we have. So we look at number of electron groups. And we look at the hybridization scheme. So if we have two groups, then it's going to be sp. We'll have two sp orbitals for those two groups. If we have three groups, then it's going to be sp2. We'll have three sp2 orbitals. If we have four groups, then it's going to be sp3. And we'll have a total of four sp3 orbitals. Five groups, it's going to be sp3d. 5 orbitals there. In 6 groups, we'll have sp3d2. So we'll have 6 orbitals to accommodate the groups. So we're going to start off with the simplest hybridization. We'll come back to water when we get to 4 groups, I think. Okay, example of the groups. We have different kinds of groups. So we'll have a single bond group. We'll have a double bond, A's for atom. We'll have a triple bond group. Single bonds are the longest, double bonds are a bit shorter, and triple bonds are the shortest. Then we'll have a lone pair group. And then we'll have a radical group. And so a group of electrons are any one of these. If I have a lone pair, I keep them together. I don't call that 2 groups, I call it 1 group. I'll call it the lone pair group. If I have a triple bond, I don't call that 3 separate groups, I just call that 1 group. Of electrons. Then there are going to be certain repulsions. Single bonds will have the weakest repulsions. Double bonds will have greater repulsion. Triple bond should have the greatest repulsion because it's got the most electrons. Lone pairs are about equivalent to double bonds, and radicals are close to equivalent. Double bond. The greatest repulsion will be the triple, followed by the lone pair and the double bond, followed by the radical, and then the weakest repulsions will be the single bond. That's because the electron cloud is more concentrated. Like in the triple bond, you have 6 electrons concentrated. Now, we only have 2 electrons in the lone pair, but it's got greater repulsion than the single bond because all the electron cloud is on atom A, whereas in a single bond, the atoms are in a tug-of-war for the electrons. What atoms are in a tug-of-war? Well, we have atom A and atom B. And so atom B is trying to pull the electron cloud away from atom A, and atom A is trying to pull the electron cloud away from atom B. And so with that tug-of-war, it means that the electron cloud isn't concentrated on a single atom. All right, so what we're going to do is we're going to look at some examples here. BeF2 is our first example. Let's take a look at beryllium. Beryllium is the second shell, or second period, so it's helium, and then we have 2s. How many electrons does beryllium have in its valence shell? 2. According to Aufbau, we'll put both electrons in the lower energy 2s orbitals versus the higher energy 2p orbitals. If we put both electrons in the 2s orbital, how many bonds should beryllium form? Can a fluorine come here and share the electron? No. So we expect to form 0 bonds. However, we can violate the Aufbau principle by promoting an electron here, which is fine. It's just called an excited state versus the ground state. The ground state would have both those electrons down here, but if we take one of these and excite it to a 2p, then we'll have 2 unpaired electrons. And so what we call this is we promote an electron to maximize bonding. Now how many bonds can I form? I can form 2 bonds. That is, a fluorine can now come in here. Actually, it should be green. A fluorine can come in here and bond here, and another fluorine can come in here and bond here. So if we look at the beryllium here, I'll have a 2p here. Let's look at that first. I'll draw a 2p here. So that's one lobe, here's the second lobe. And I'll put 1 electron in there, spin up. And then I'll look at fluorine. When I look at fluorine, fluorine is the same. It's going to be helium, 2s, 2, 2p, 5. I'll have to do this last one spin down. So that beryllium can come in here. Beryllium can come in here and bond to this orbital here. And so fluorine is going to bond to beryllium here using a 2p orbital on fluorine here. All right, is the 2p orbital on beryllium the same size as the 2p orbital on fluorine? Are all 2p orbitals the same size? No. Which one is smaller, fluorine or beryllium? Well, first, let me ask you, which atom is smaller, fluorine or beryllium? This is for chapter 9.
This one here and this one
Okay, thank you. Okay, which atom is smaller, fluorine or beryllium? Fluorine's smaller. Why is it smaller? Why is fluorine smaller than beryllium? It's got more stuff. If it's got more stuff, shouldn't it be bigger? Should be bigger, but one of the key things it has is more protons. And the protons act like a, you know, in sci-fi they have the tractor beam. You know, tractor beam will pull in ships or whatever. That's like it. The more protons, the stronger the tractor beam for electrons be. And so it's going to pull the 2p electrons closer. And therefore its 95% probability boundary is going to be smaller. And so this will be a 2p orbital on fluorine, which is smaller than the 2p orbital on beryllium. It doesn't have as many protons. And we have a name for this in valence bond. In valence bond theory, we call this a 2p sigma bond, or pp sigma bond. All right, that's this one here. All right, what about the other one? We have a 2s on beryllium. This is beryllium. The 2s is not directional. The 2s is spherical, like this. And so the other fluorine can come anywhere along the sphere. Could we put it right next to each other? So the two fluorines are right next to each other. Should we do that? No, we shouldn't do that because, you know, the overlap region is a region of increased probability. And so where the orbitals overlap here, we see a greater negative charge density, greater electron cloud. So if we put them right next to each other, we're going to have two regions of greater negative charge density. And negative repel. And so they don't want to be next to each other. But if I crank it over to the opposite, and I put the fluorine here, that poses a problem. Because if I put the fluorine here, then the fluorine orbital can overlap with the other lobe of beryllium. And is it possible to put 3 electrons into one orbital? No. I don't want to put it here. So I got to find some other place to put it. And so this one, we'll just put it, let's say put it here. So this is a 2p bonding to the 2s. And so this would be called a 2p 2s sigma or a ps sigma? And the shape is a little bit kinked. You see the shape is going to be kinked depending on what angle this fluorine is. It's going to be a little kinked. Maybe something like this. But is this correct? I got these other two empty orbitals here. You see that? I have these other two empty orbitals here, but I have no electrons there. Why not double bond? Is it one of the problems with this structure is beryllium, does it have an octet? No. Do you see its valence shell is not filled? How can I fill the valence shell? One way I could fill the valence shell is by forming double bonds. But what's the problem with forming double bonds? They're shorter. That's not a problem. They can be shorter. That looks pretty good because it has an octet, but there's a problem. And the problem has to do with the formal charge. What are the formal charges that result from this? The formal charge on this fluorine is lone pairs belong entirely to fluorine. 1, 2, 3, 4, and then formal charge we split the bonds evenly. So 1, 2, 3, 4, 5, half of this, and 6, half of this. So that's 6 electrons. Fluorine donated 7 electrons to this structure. So this is going to be plus. This fluorine's the same at plus. This beryllium is going to be minus 2. It donated 2 electrons and ended up with 4 electrons. Does that look like a good formal charge? If there's a tug of war between beryllium and fluorine, not just 1, but 2, this beryllium is very strong because it can battle 2 fluorines and win. Do you think that's likely? No, this is highly unlikely. And so in order for beryllium to get an octet, fluorine has to donate 2 electrons here. And so fluorine would form a single bond and then donate another pair of electrons here and another pair of electrons here. And then beryllium can get an octet, but that's too many electrons for fluorine to donate. And so we come up with a rule: fluorine never forms double bonds. Because in order for fluorine to form double bonds, it has to give up an electron. And it's not going to do that.
Is that true in real life? Is it true in real life that fluorine will never form double bonds?
In real life, yeah, fluorine does not form double bonds. Fluorine does the other strange stuff with bonds, which we're not going to talk about. But this is it. So we're kind of stuck here. All right, which brings us to another point. That is, these two fluorines want to be on opposite ends of the structure. And so we're going to do one more step here. The one more step that we're going to do is we're going to take the S and one of the P's and come up with hybrid orbitals here. And so we're going to hybridize. The reason we're going to hybridize is to minimize repulsions. So we're going to take a 2s and a 2p orbital and hybridize that. When we hybridize it, we end up getting two new orbitals. Called sp orbitals. Sp orbitals have two lobes, but they're lopsided. One lobe is big, the other is small. So often what we do is we ignore the small one and just focus on the big ones. And it's going to be half S, half P. So it's going to be higher in energy than the S, but lower in energy than the P. And it's going to be midway, the midway point energetically. And so this will be the SP hybrid, SP hybrid. This will be unhybridized P, unhybridized P. So we'll have this situation. When we look at this, we can draw out the orbitals here. So we draw an sp orbital here, and then another sp orbital here. It looks like a p orbital, but this is two separate orbitals. This is not equal to a p orbital. A p orbital would be one orbital with two lobes. This is actually two orbitals with a total of 4 lobes, but the little lobes aren't shown here. Knock those off. And then there are two unhybridized p orbitals. One p orbital looks like this, and so this would just be one p orbital versus two sp orbitals here. And the other p orbital would be orthogonal to this. So we're going to have another p orbital with the lobe sticking out, and then a lobe going in. So those would be our unhybridized p orbitals. Now what can happen is fluorine can come in and bond here. So fluorine comes in to bond here, fluorine comes in to bond here, to beryllium. And we end up with this. This sp orbital will put the spin up, and then we'll throw in fluorine in here. Fluorine has smaller orbitals. This is Z here. And so this would be a p orbital on fluorine, not an sp. And then on the other side, the opposite side, we have another electron. So this is not 2 electrons in one p orbital. There are 2 electrons in 2 separate sp orbitals, so I'll label that sp here. And then this is going to overlap with this other fluorine over here. And this would just be one single p orbital here. And so the bonds we have are p-sp sigma bond. P-sp sigma bond. And this would be an sp-p sigma bond. And the bond's going to be held together by the increased cloud density in the internuclear region here versus over here. And so that's what's going to hold the two berylliums. And so we end up with a structure that looks like this. I didn't draw the p orbitals in there. P orbitals aren't participating. And so we have beryllium, this two fluorine. The orbitals are going to be 180 degrees relative to one another. It's SP. What is more electronegative, fluorine or beryllium? Fluorine or beryllium? Fluorine. So what that does is it biases the electron cloud here. Yes, there's increased electron cloud density in the internuclear region, but it's going to be more towards fluorine in both these cases. What that means is that the electron cloud is polarized towards fluorine. We call fluorine delta minus, beryllium delta plus, and this fluorine will be delta minus. And that creates something called bond dipoles here. But these bond dipoles are equal and opposite. And so the electron cloud is polarized towards fluorine. But when we add these up, we get 0 dipole moment. Dipole is a positive and negative pole. And so beryllium difluoride is weird. You'd expect beryllium difluoride to be an ionic compound. It's actually molecular. This occurs with molecules. Okay, the next structure we're going to look at is CH2O. CH2O is called formaldehyde. It's a liquid. It smells awful. Formaldehyde. Carbon has 4 electrons, 2 hydrogens is 2 electrons, and oxygen is 6 electrons. So altogether we have 12 electrons. So we try to come up with a skeleton for this. How does that look? That doesn't look right. Let me fix that. How does that look? Does that look good? Is formaldehyde an acid? Yes or no? No, formaldehyde's not an acid. How could you tell? How you could tell is if it were an acid, it would start with the letter H. It doesn't. It's not an acid. This is acidic because the hydrogen is bonded and most electronegative. I don't expect that. Instead, let's generate a skeleton like this. So far we've used up 2, 4, 6. Let's complete the octet to oxygen. 8, 10, 12. That's 12 electrons. How does that look there? It doesn't look good. It doesn't look good because we don't have an octet on carbon. In order to make an octet, that's easy. We'll just take a lone pair, convert it into a bonding pair. If we do that, then we end up with this structure. How does this structure look? Well, as far as octets go, this is good. Hydrogen doesn't get an octet, though. It never does. It gets a duet. And so this is good. What are the formal charges? All the formal charges are 0. So this is a good structure. And now we're going to do valence bond analysis. Carbon is second shell, so first shell is helium, and we're going to get the 2s and then the 2p. Carbon has how many valence electrons? 4. So off bow says filled lowest energy first, so 1, 2, 3, 4. How many bonds should carbon form? How many bonds does it look like carbon can form? 2. That's not enough. We have 2 singles and 1 double. So what should we do? What do we need to do now? We need to promote. We promote to maximize bonding. Now, how many bonds can I form? 4. But when I look at the bond angles, if I use these p orbitals, the p orbitals are 90 degrees, right, with respect to one another. And so I'd expect bond angles of 90 degrees. Well, that's not what's observed here. And so what I'm going to do is I'm going to promote electrons to maximize bonding, and then I'm going to hybridize to minimize repulsions. What I hybridize depends on how many groups of electrons I have around carbon. How many groups of electrons do I have around a carbon? I have 4 groups or 3 groups? I have 3 groups. I can't split the double bond apart into 2. And so around carbon, I have a double bond, that's 1 group, and 2 single bonds, that's 2 more, so it's a total of 3. And so I'm going to hybridize this sp2. And so I'm going to use the s's and 2 out of the 3 p's. And so I'll end up with something that looks like this. I'll get 3 equivalent sp2 orbitals. Those 3 are going to be closer to closer to p than s in terms of character. And then this p orbital is untouched. This p orbital stays as is. So in these 3, I'm going to have 3 electrons, and then we'll throw 1 more up there. I think I skipped one. Did we do BF3 before this, or BF2? We didn't do BF3? Skipped it. So what I'm going to do is I'm going to draw out the orbitals. When I have sp2 hybridization, this is what it's going to look like. I'm going to take an S and hybridize it with 2 p orbitals. 1 p orbital I'll draw like this, and another p orbital I'll draw like this. There's yet a third p orbital, that I'm going to leave alone. This will be the third p orbital here that I'll leave alone. Because of the phase, that is the plus minus aspect of these orbitals here, this is what it's going to look like in the end. I'm going to get 3 equivalent orbitals. Each of these is called an sp2 orbital. The angle between these orbitals is going to be 120 degrees. And then I'll have 90 degrees with respect to this p orbital that's stuck in the center here. It'll be 90. And what I'm going to do is I'm going to call this top view here. Then I'm going to draw a side view of this by rotating this. So I'm going to call this an axis, rotation axis here, rotated 90 degrees, like this. If I rotate this 90 degrees, then I'll have this sp2 here, but this sp2 is going to stick out of the page, or the plane. And this sp2 here will stick in to the plane. But what we're going to see is the p orbital. The p orbital is going to be, you're looking at it from the top down, now you're going to look at it from the side. And so this will be the p orbital here in profile. So that's my side view. So I'm going to come back to formaldehyde, but let's do a simpler example first of this. A simpler example would be BF3. BF3, boron has 3 electrons, fluorine has 7 times 3. 3 times 7 is 21 electrons. That gives us a total of 24 electrons. And so fluorine can never be in the middle. Fluorine's always going to be on the end. And then we'll complete the octets to the 3 fluorines. And then we run out of electrons. But the problem is boron doesn't have an octet. Can I form a double bond? No. And so I'm stuck. I'd like to double bond, but this is not going to work because that would mean fluorine would have to give up an electron to boron. Unhybridized, boron is going to be seconds, so it's helium, core, 2s2, 2p, 1. Unhybridized boron can form how many bonds? Only 1. We don't have to hybridize, we could just promote. If we promote an electron, then we can form 3 bonds. However, the bond angles are going to be 90 degrees. With the bond angles of 90 degrees, we get larger repulsions. And therefore, we're going to hybridize to try to minimize the repulsions. We're going to hybridize it sp2. And that's going to leave 1 p orbital unhybridized. All right, now the 3 fluorines can come in and bond here into our sp2 orbitals. The sp2 orbitals are going to be oriented at 120 degree angles. And so I'm going to have a fluorine come in here, bond, 1 come in here and bond, 1 come in here and bond. The p orbital stays empty. So let's draw that here. So I'll have a boron, and then I have 3 sp2 orbitals here. This will be an sp2 orbital, and then another sp2 orbital at 120 degrees, and then another one at 120 degrees. And each one of these has one electron. And then we'll have the fluorine come in and bond. Fluorine's p orbitals are smaller. And so I have one fluorine bond there, another fluorine bond here, yet another one bond here. We have a p orbital there, but it's empty. And that p orbital here, looking, this is a top view, looks like this. It's empty. And so what we form here are p sp2 sigma bonds, or sp2p sigma bonds. The angle between them should be 120 degrees. Yeah. All right, let's go back to formaldehyde. So going back to formaldehyde, when we look at carbon, which has 4 valence electrons, no lone pairs. And so in carbon, we don't have an empty p, we have an occupied p. And so we'll draw that. We're going to draw our 3 sp2 orbitals, like this. Each of our sp2 orbitals will have a single electron. And then we'll draw our unhybridized p orbital here. This unhybridized p orbital will have a single electron there. Two hydrogens come in here and bond. So one hydrogen is going to have one s orbital spin down. Another hydrogen here, one s spin down. And so we're going to form sp2 sigma bond to the hydrogen. And then finally the oxygen is going to come in. But we have to take a look at the oxygen next. We have a choice. Our book doesn't hybridize the terminal atoms. I'm going to hybridize the terminal atoms. And so when I look at the Lewis structure here, I come up with something that looks like this. And I see that carbon has 3 groups, 2 singles and a double. Oxygen also has 2 groups, 2 lone pairs and a double. So what I'm going to do is I'm going to hybridize oxygen as well. So if we look at oxygen, it has 3 groups. Therefore, we're going to call it sp2 hybridized. And then it's going to have one unhybridized p. Now, how many valence electrons does oxygen have? Well, in this structure, it has 1, 2, 3, 4, 5, 6. So it has 2 lone pairs. We fill the orbitals according to the Lewis structure. So I got 2 lone pairs, and then that leaves me with 2 more electrons for a total of 6 electrons. So it's going to look like this. All right, so I'm going to write out the oxygen up here. Okay, which is going to have smaller sp2 orbitals, oxygen or carbon? Oxygen. So I'm going to write my three sp2 orbitals like this: sp2, sp2, sp2. Two of the sp2 orbitals I have lone pairs, so I'll put the lone pairs in these. And one of them, I have to flip the spin. You see the spin? I can't have it spin up. It has to be spin down. It has to be spin down because it's going to form a bond here with carbon. And so this forms an sp2 sigma bond. So in other words, this. Oxygen comes in here with an sp2 and forms a sigma bond here. Or the other way of thinking about this is that carbon comes in here with an sp2 and forms a sigma bond here. So sp2 sigmas, depending on if we're looking at it from carbon's perspective or oxygen's perspective. But we have this p orbital here with one electron and p orbital here with one electron. And what happens is these are oriented so that the lobes on the top can overlap and the lobes on the bottom can overlap. And so what we're going to end up with here is I'm going to have to make this spin down now. The oxygen. Because the p orbital on oxygen is going to come over here and overlap with the p orbital on carbon here. And so this forms a pp pi bond. Now, the difference between a sigma bond and a pi bond is this. Well, actually, let me show you in a minute what the difference is. Carbon is going to come in here with its p orbital here, and then bond here. And so we'll have the pp pi bond on carbon's perspective and oxygen's perspective. All right, this is top view. Now I'm going to rotate this for a side view. So I'm going to take that molecule, rotate it 90 degrees along a vertical axis. So if I do that, I'll have oxygen here, carbon here. And so I'll have this sp2 sigma bond here. But it's going to throw out this sp2 coming out like this. And another sp2 going in. This is sp2, sp2, sp2. And these will be singly occupied, and then the hydrogens will bond to this. And then the lone pair here is going to stick out. So lone pair here, and another lone pair is going to stick in like this. Well, what it's going to do is it's going to show the p orbitals in profile. So now I'm going to have a p orbital here. On oxygen, and the p orbital on carbon here. And even though they don't look like they overlap, they do. This is just a boundary. Electrons can extend beyond the boundary. So there's overlap on the left side here and overlap on the right side. Over here, that overlap is shown as overlap on the top and overlap underneath on the bottom. And so this is one pp pi bond. Now the difference between a sigma bond and a pi bond is this. A sigma bond has overlap within the internuclear axis. So what I do is I'll draw an axis connecting both nuclei. So one nucleus is here, one nucleus is here. And so the sp2 sigma bond has overlap within the internuclear axis, whereas the pp bibond has overlap to the left of the internuclear axis and to the right, but no overlap in the internuclear axis. And so that's the difference between a pi bond and a sigma bond. Here. Okay, these two bonds equals the double bond. A double bond is 1 sigma and 1 pi. A triple bond would have 1 sigma and 2 pi. All right, so let's build these here now. So on the model kit, take a look at the inside cover. There's a photo of how the atoms should be arranged. There's also a photo of how the sticks should be arranged, but you could ignore it because are your sticks arranged like that? No, so you don't need to arrange them like that. Okay, but we need to arrange the atoms like this. And so the first molecule we're going to build is beryllium difluoride. So take out the silver ball. And then attach 2 long sticks to it on opposite ends. And then attach 2 green balls to that. And once you do that, you have beryllium difluoride. Beryllium difluoride should be ionic, but it's not. It's molecular. Yeah, and then imagine the bonds. One bond is going to be an sp on beryllium, the silver, overlapping with a p on fluorine. We have an spp, and the other will be an spp too. And the sp orbitals are oriented 180 degrees relative to one another. Okay, the next one we're going to build is boron trifluoride. So get the brown ball. The brown ball has 5 holes. So look for the holes that are opposite one another. And you can pinch those. And then to the 3 holes in a trigonal planar arrangement, attach 3 long sticks to that. And then 3 green balls. All right, so this is boron trifluoride. Boron trifluoride has 3 sp2 orbitals that are oriented at 120 degree angles and 1 unhybridized p. The unhybridized p will be perpendicular. Here, it would be the spinning axis. The unhybridized p orbital is empty. We have less than an octet. Next, we're going to build chloroform. Get a black ball, stick 2 long sticks and 2 short sticks. To the 2 short sticks, put 2 white balls. Those are the hydrogens. And to the 2 long sticks, put 1 red ball. And so you're going to have to bend the long sticks so that you can attach them both to 1 red ball, like this.
Yeah, I have a bigger.
Yeah, that's it. And so this is chloroform here. This would be the top view. This would be the side view. And so the double bond here is represented by the two long sticks. In the double bond, you'll have PP pi bond. The two long sticks kind of represent the two PP pi bond. But you'll also have an sp2 sigma bond, which should be straight between these, but you don't see any stick here. So the sp2 sigma bond's not shown here. But anyway, the two sticks represents a double bond. All right, just a couple more things to say, and then we'll stop. But let's look at bonding environment. Sometimes you could use these as like little shortcuts. So carbon likes to form 4 singles, 1 double, 2 singles, 1 triple, 1 single. This is neutral carbon. If carbon has a positive formal charge, then it likes to form 3 singles or a double and 1 single, but it's missing an electron here. These are carbocations, we call them. If carbon has a negative formal charge, then it ends up having a lone pair. So you have a lone pair and 3 singles, a lone pair and a double and a single, a lone pair and a triple. So that's a carbocation, carboanion. This is just plain carbon. And then we have a radical, carbon radical. The carbon radical could be like 3 singles here, a double and a single, or a triple. That would be a radical. There's no formal charge on that. Nitrogen likes to form 3 bonds. So nitrogen usually has a lone pair and 3 singles. Or we could have nitrogen with a double and a single and a lone pair. Or we could have nitrogen with a triple and a lone pair. We could also have nitrogen with a positive formal charge. Nitrogen with a positive formal charge will form like 3 singles. There will be a plus charge there. Or, actually, no, that won't be a plus charge, will it? No. Or 4 singles. Etc. This would be plus 2. Let's get rid of this one. All right. Yeah, just that one is pretty much it. Nitrogen with a negative formal charge is going to have a lone pair. Not just 1, but 2 lone pairs and 2 singles usually. Or 1 double. But these are the 2 most common that you see. Oxygen likes to form 2 singles or 1 double. When oxygen forms 2 singles, we call it bridging oxygen. When oxygen forms a double, we call it a terminal oxygen. But there are other bonding environments. So for example, if oxygen has a positive charge, then typically what we see are 3 bonds to the oxygen, giving it a net positive charge. Or oxygen could have a negative charge, in which we'll have 3 lone pairs in a single, giving it a negative charge. So we'll do one more structure and leave it at that. The last structure we're going to do is carbon monoxide, CO. Carbon has 4 electrons, oxygen has 6 electrons, so that gives us a total of 10 electrons, valence electrons. And so we'll do it. We'll complete the octet to the oxygen first. So that's 2, 4, 6, 8, and then 2 more electrons gives us 10. But does this structure look very good? No. So what we're going to do is we're going to form a double bond. Is a double bond enough? A double bond's not enough. So we're going to have to form a triple bond, and then it's enough. So if we form a triple bond, then everybody has an octet. But what's the problem with the triple bond? The problem with the triple bond are the formal charges. What's the formal charge on carbon here? -1. The formal charge on oxygen?
+2.
Not +2. It has 1, 2, 3, 4, 5. It's supposed to have 6, so it's just +1. That's a problem. And so we might back this off. If we just go with a double bond, like this, then there are no formal charges. Carbon has 1, 2, 3, 4. Oxygen has 1, 2, 3, 4, 5, 6. So the formal charges are 0 and 0. But the problem is carbon doesn't have an octet. And so what's more important? Carbon having an octet, but with this weird formal charge arrangement, or carbon not having an octet? It turns out this is not observed. This is observed. So octet rule wins here, and so we end up with a weird formal charge. This weird formal charge gives interesting properties to carbon here. This is a strong Lewis base. A strong Lewis base attacks Lewis acids, such as hemoglobin. And that makes carbon monoxide especially toxic. Its Lewis base properties are too strong. And disrupts normal functioning of hemoglobin. But anyway, this is going to be sp hybridized. So carbon's sp, and oxygen is sp. So if we have sp hybridization, there are 2 sp orbitals, and then we have 2 unhybridized p orbitals for carbon. And for oxygen, we have 2 sp orbitals. Oxygen's sp orbitals are smaller and lower in energy, and 2 unhybridized p orbitals. Now we have to look at how many electrons does carbon have in the structure. We filled this based on the structure. So I see carbon has 1 lone pair. I'll just throw that in here. And then how many more electrons do I have for carbon? So I have 1 lone pair and then 3 bonding electrons. Do you see that? 1 lone pair, 3 bonding electrons. 1, 2, 3. Okay, that fills up the orbitals there. Then I go over here to oxygen. How many lone pairs on oxygen? 1 lone pair on oxygen, I'll throw it here. And then how many bonding electrons? 1, 2, 3. And so this is going to be resulting in a carbon with a negative charge. Carbon normally has 4 valence electrons. I count 1, 2, 3, 4, 5. So it has an extra electron, giving it a negative charge here. Oxygen normally has 6 valence electrons, but how many do I count? 1, 2, 3, 4, 5. So this is a positive oxygen. It doesn't have the normal number of electrons. And so what we're going to do is we're going to build this out here. With sp hybridized orbitals, I'll draw the carbon here, and then I'm going to draw an sp orbital here. And then I'll draw an oxygen here. The sp orbital on oxygen is smaller, lower in energy. And then I'll make I'll make carbon's sp spin up. Therefore, I have to make oxygen's sp spin down. So let me change this to spin down here. And then I'm going to form a bond here. So to the carbon, an oxygen's sp orbital is going to come in here and bond here. On oxygen's perspective, a carbon's sp orbital is going to come in here and bond here. So what we end up with is an sp-sp sigma bond. Okay, then I have another sp orbital here with a lone pair. And then another sp orbital here with a lone pair. And so that takes care of these lone pairs here. All right, now I have to deal with the p orbitals. And so let's take a look at this first p orbital here. This first p orbital I'm going to write as a side view here. And oxygen's p's are smaller. So this p orbital I'm going to put spin up on carbon. And therefore, excuse me, is this ox? Yeah. On carbon. And the p orbital on oxygen I'm going to make spin down like this. So what's going to happen is, even though they don't look like they can overlap above and below here. That forms one bond. So this is a p-pi bond here. And so from carbon's perspective, an oxygen with a p electron comes in here, bonds here. And carbon with a p comes in here and bonds here. It's the same atom. And so we now have a double bond. The triple bond comes about by looking at the next p orbital here, and this one. Okay, these p orbitals are going to be perpendicular. And so for carbon's p orbital, I'll put spin up. For oxygen's p orbital, I'll put spin down. Down. And then we're going to have overlap above and overlap below the plane, the board. And so this will be the final here. And so that's going to be the triple bond. We're going to overlap 3 atomic orbitals for each atom. And that results in the triple. On here. A triple bond consists of 1 sigma and 2 pi's. All right, I'm going to stop here, and then we'll take a break.